Right. So today's topic is going to be analysis and design of beams, and it's a topic that we're going to integrate mathematics and physics. Okay, so you have to be really sound with your math. Okay, and it's not difficult math. It's not the sort of integration that you do in your 3MA3. Okay, it is simple math. But the thing is, you have to analyze. Okay, you have to analyze your equation. It's not just okay, I've got this equation, that's it. Okay, you have to analyze. So we're going to do design analysis and design of beams. So the first thing I'm going to go through is we're going to look at shear force, right, which is V, and bending moment diagrams. And when you see the shear force, where are we going to use shear force on? So we already learned that we can find the shear stress of the beam, which is equal to VQ over IT, right? And from the bending moment, we can calculate our normal stress, which is equal to MY over I. So the shear force is will get you the shear stress, and the normal stress is from the bending moment diagram. Okay, so that's why we are doing this for. Okay, so we know how to use the shear force and bending moment. Okay, with those formulas that I've just shown, but how to acquire the shear force and bending moment. Okay, so I'm going to do this directly by looking at an example. Okay, by looking at example. Okay, so let's look at an example. So this example is we're going to form the shear stress or shear force and bending moment equation. And then we are going to sketch the, again, shear force and bending moment diagram. Okay, and then from here we are going to select the beam, okay, based on the analysis. Okay, you will select the beam. Okay, so that's what I want to capture over here. So let's look at the example. So this example over here, what we have is a beam that's overhanging. So we have a overhanging beam. Okay, let me draw better. So we have a overhanging beam. So this overhanging beam, I'm going to label the positions. So you have point A, and then somewhere down here you have point B. So at point B, you have a pin, and then you have point C. Point C, you're on a roller, and then we have our point D. Okay, then we have a transformation X, Y. This is rotation about Z. So this is a overhanging beam. And then at point A, you have a load P. And at point D, you have another load D. And then between B to C, you have an evenly distributed load. Okay, you have an evenly distributed load. So that is our evenly distributed load. And our evenly distributed load is W or omega Newton per meter in terms of units. And then we have our respective dimension. So from A to B, you have A. From C to D, again you have A. And then from A to the entire distance, D, what you have over here is L, right? And then from here to here, you have L minus A. Okay, you have L minus A. So always remember the datum will be taken from the left-hand side in all the analysis. I repeat again, in all the analysis, the datum will be taken on your left-hand side. So the datum, yes.
Shouldn't it be 2A?
Oh, yeah, right. Thank you. Okay. You're right, it's 2A. So L minus 2A. Thank you. So from here, again, your geometric datum, okay, will always be on your left-hand side. I'll explain to you later why. Okay, so this is your geometric datum. And then I want you to learn boundary condition. Okay, so we have at point B is x is equal to A. Okay, and at point C, x is equal to L minus A. Okay, and there are sequence of symbols that I want you to remember, and later on I will explain to you why, or probably next week. So we will have V, M, theta, Y. Likewise, for this case, you also have V, M, theta, Y. Okay, so I want you all to remember the symbols in this sequence. Okay, V, M, theta, Y. I want you to remember now. Okay, I'm not going to tell you why until I teach the next topic. Then you'll see why we're relating this. So the V is our shear force. Our M is bending moment. Our theta over here is the slope or angle of deflection. Or slope. And then finally, your Y is your Y displacement due to deflection. Okay. So all this down here, what you have seen down here, right? V is the shear force at point C and point B and point C. What are the shear force? We don't know. Okay, if you don't know, don't write anything. How about the moment at point C, point B, and point C? We also don't know. Slope, we don't know. But one thing for sure, deflection is equal to 0 at point B, and at point C, deflection is also equal to what? 0. So in this context, over here, what we have done down here is this is known as our boundary condition. Okay, these are boundary conditions. So boundary conditions are a mathematical representation of what is happening physically. So at point B, we know that deflection in Y has to be equal to 0 because you have a support at point B. Likewise, at point C, where X is equal to L minus A, the deflection at Y is also equal to what? 0. Okay. So from here, we would like to form the shear force and bending moment equation. And then we're going to directly sketch the shear force and bending moment diagram. Okay, so that's what we're going to do now. Okay, so the first thing to do to enable to do your shear force and bending moment diagram, you have to perform static analysis first. Okay, so we're going to do static analysis. To determine the reactions at point B and point C. Okay, so again, I'm going to sketch our structure out, right? So this is our point A, our point B, our point C, and our point D. Okay, so when doing this, you have to make sure that you put in your reaction and what is the force applied. So the first thing we do, so we have P over here, we have another P over here, right? And then we have a reaction. So this is By, and then we have a reaction down here, Cy. By right, we also have a Bx, but we know that Bx will be equal to 0. And then over here on the center, right, between B and C is our equivalent load. So I've mentioned this equivalent load before, so it's equal to omega bracket L minus 2A. Okay. And then the next thing we're going to sort out is all our distances. Okay, so we try to put in our distance. So we have our from here to here, right? We know that this is our A. And then the distance from here to here, okay, is L over 2 because it's midway, right? And then the distance from here to point C is equal to L minus A. Okay, so we realize on this structure over here, right, if I draw a vertical line from the center, right, the left hand side is equal to the what? The right hand side. Okay, so I'm going to call this YY line, right? So from here, based on this analysis, okay, so from here, based on symmetrical loading and geometry, right? So you have to satisfy both, where the symmetrical is not just the loading and also the geometry about the line YY. Okay, so what we discover here, so therefore By is equal to what? Cy. Okay, so we have By is equal to Cy. So from here, we can immediately go for summation of forces in the y direction is equal to 0. So you have minus P plus by By, right? Then you have minus omega L minus 2A plus by Cy minus P, the whole thing will be equal to 0. Okay, so because the fact that By is equal to Cy, you will write this as 2By, right, minus omega L minus 2A minus P, the whole thing is equal to 0. What we have done is we have replaced Cy with what? By. That's why we call it 2By. So therefore,
it's 2P.
2P. Oh yeah, I'm done today. I'm losing money today. Thank you. Is equal to 0. Okay, so you have By over here is equal to omega over 2 L minus 2A, and then plus by P. Okay. So that is your By, and because By is equal to Cy, so you also By is equal to Cy. Okay. So this is